So this row reduction algorithm that we talked about in the last lecture, this is great. It's the tool that we need. Um, but so far, it hasn't really answered the question, because our question was, how can we find the solution to a system of equations? Right. So we do kind of have one more step to go, seeing how we can take that final result and transform it into the solution set that we're looking for. Okay, so before we do that, this will be the last set of this will be the last set of definitions we need for this process. I do have two more definitions here. Variables corresponding to pivot columns are base variables. Okay, so looking at this example here, variables x1, x2, and x3, those correspond to pivot columns, so those will be the base variables. Variables corresponding to non-pivot columns, like column 4 here, those are what we're going to call free variables. We'll talk a little bit about why when we get a little further in here. So here is our actual method for solving systems of linear equations. First, write the augmented matrix of the system. Right? Convert the system to a matrix. Second, use the row reduction algorithm to rewrite that augmented matrix in its reduced echelon form. Step 3, go backwards. Take that reduced echelon matrix and convert it back to a system of equations. Finally, rewrite each non-zero equation from 3 so that its one basic variable is written in terms of any free variables. Let's look at some examples. Right, this one here, this is kind of in some ways, it's kind of the ideal case. Right? In this case, there are no free variables. There's 4 variables because we've got 4 columns plus the augmented one. And each one has a 1 for a pivot. So if we rewrite this back to a system of equations, we get x1 equals 3, x2 equals 6, x3 equals 1, x4 equals 2, and that one point, if you will, the one point in 4 dimensions, is the sole solution to the system of equations. Okay, so how about this situation? Now we do have a free variable. All right, variable 4 is a free variable. So how is this going to work? Well, go through the process. Right, we've already made it to step 3. We have our reduced echelon form. So I'm going to convert this back to a system of equations. Right, x1 plus 3x4 equals 3, x2 equals 6. Great, single number for that one. X3 plus 2x4 equals 1, and x4 is the free variable. So what that last step is saying is x4 is the free variable, right? So take all of the other 3 equations and solve them for something in terms of x4. Right? So I'm going to move both of the x4 terms in each of the 2 equations that have them over to the other side, and there's my solution. Right? This system of equations describes the solution set. So, and if you look at this, you can kind of see why we call x4 a free variable. x4 can take on any value you want, any real number, negative infinity up to plus infinity. Pick a value for the free variable, substitute it into these equations, and you get a solution to the original system. Right, so what we have here is an example of what's called a parameterized system, right, where x4, the variable that we've solved in terms of, that's the parameter. Now, there's nothing magical about the free variable. Okay, this is the system we were looking at on the previous slide. I could take these equations, solve the first one for x4, right? So now I have x4 in terms of x1. Then I can take that formula for x4, substitute it into the x3 equation, right? If I do that, x4 is still equal to negative x1 over 3 plus 1. x2, bless x2, it's always going to be 6. And now I have x3 in terms of x1. So now I have a different parameterized solution. Right? I've rewritten this so that x1 is the parameter instead of x4. They're both perfectly valid results. Right? Like I said, there's nothing inherently special about the free variable. However, for our purposes, just for the sake uh, of internal consistency, this is how the first solution is how I'm always going to do these, right? When it comes up, I'm always going to solve for the base variables in terms of the free variables. So this brings us to the end of our discussion of solving systems of equations, although a lot of these methods are going to continue to come up as we get deeper into the course. So from here, you've got two paths you could follow. One outstanding question that we haven't addressed, and one that's very dear to mathematicians, is the question of existence and uniqueness. How can we tell when a system has a solution, and how can we tell when that solution is unique? Now, those are two very theoretical questions. So if you aren't really interested in that aspect of the material, that's fine. You can skip to the other video linked here, where we're going to start talking about a special kind of matrix called a vector.